All right, we're going to go ahead and get started. If you're interested in track 2, that is upstairs. This is track 1, and this is the first workshop. And I'm pleased to present Dr. Aryeh Weiss. Thank you, Dr. Weiss.
Thank you. Still didn't do what I wanted to do. All right, thank you. Okay, this is the introduction to digital image processing. And you already know I am, so I'll go to the next slide, please. And the purpose of this is really to give you some vocabulary and orientation for many of the other presentations, workshops, and so on that you will that you will hear. There's about a semester worth of material here, so you probably won't cover it all, but since these slides are available online, I thought it a good idea to include it so that you have that available. And it's not so much interactive. Feel free to ask questions in the during the presentation. We'll kind of look at how the time is going and edit accordingly. In this audience, I don't think I have to explain to you why you'd want to use image processing. Most of you are here because you already know why you want to use image processing, but the bottom line here is pretty important, so I put it in. Image processing is what you do after the acquisition is optimized, okay? Image processing does not restore poorly acquired data, and we could do another workshop on image acquisition and what are the right ways to do that. I'll say a few words about that here. Now, about maybe a third to half of this workshop will be about image formats and what is a digital image. I think that if you know what a digital image is, then much of what you see done with them becomes more intuitive. And I've seen also from the mailing list a lot of confusion. What's this 8 bits and 16 bits in dynamic range, and how come the scale, the display suddenly changes its intensity and so on. So we're going to be talking about representations of digital images, a little bit about how digital images are stored, and how digital images are characterized. And that's really the most important thing that we must do. And then we'll try to get into the image processing workflow and segmentation. You'll already hear more about, especially in the next talk with Jan's talk in biovoxel. So we did some coordination so that he kind of expects that I'll cover certain things in this talk so that he can continue with his. So what is a digital image? A digital image is just numbers, and that's very important. No, computers only know how to store numbers, actually zeros and ones. They're generally organized in units of 8 of these, 8 bits, and nowadays all these computers are 64-bit, which means they can grab, 8 of these at a time, and so on. But they're just numbers. And the very same numbers could be a database for grades or names or ASCII data or whatever. Now, you normally take an object, it somehow becomes an image. That's, in my case, usually a microscope of some sort, but or some camera, or maybe an atomic force microscope, or whatever, but it becomes an image, and that image might still be, optical or whatever, but then that somehow magic happens and it becomes numbers in a computer. For most of you, that may be with a digital camera. And now the numbers in the computer are discrete, so all your images are sampled. Sampling means that there's the concept of the pixel, which means that's what we'd call spatial sampling, and intensity, and that would be the number of bits in the image. People talk about an 8-bit image or a 16-bit image. 8 bits are 256 levels, which is 2 to the 8th minus 1 is 255, right? So 2 to the 8th is 256. So that's intensity sampling. It's temporally sampled. You might take a time lapse or something, and your system is capable of acquiring, let's say, 2 images a second, for example, the type of system you're doing, or 1 image every 10 minutes is, in some cases. That's temporal sampling. It could be spectrally sampled. You all know that as RGB, red, green, blue. Hyperspectral imagers. I have a friend who works on imagers that acquire, 55 spectral channels at once and works on that, and so on. But that's all sampling. And the acquisition process is very important. We won't be talking about it as much, but it's important to know that's what the image is. So this is an example of two images. They're sample images from the ImageJ site. And while this talk is not really specific to ImageJ, I developed most of the examples in ImageJ. And for fun, when you download the PowerPoint presentation, you might try to reproduce some of them as an exercise to become facile with the ImageJ. So this is what we mean. Here are a set of pixels. I've taken the boat. Okay, up here you see the, let's go previous. This is, I think, from here, one of the masts of the boat. And so we take that mast, and you can look here and see that the background, which is bright, has, values that are higher. Each one of these numbers is a pixel. And I then colored in red all the values that were below. Oh, I was supposed to color all the ones below 100, but I see I made this one wrong, and it's 121. It's still red. But you can still get the idea that this red sort of looks like the top of the mast. And notice that the blue are the intermediate values, and that's very typical of edges. Edges, you have a transition from light to dark or dark to light. Now, we're going to talk more about the fact that there's no rule that says that the brighter parts of the image have to have higher numbers. Nothing in the world says that has to be so. And we'll get to the concept of a lookup table. And if you want, you can represent white as 0 and black as 255. If it's a 16-bit image, it's 65,000 something or another because it's 2 to the 16th. Many of you have cameras that produce 12-bit images, and that's 4095, right? That's how high you get powers of 2. So, but that's the idea of it's spatially sampled, and it's also, in this case, intensity sampled because these numbers are discrete, they're integers. So here we have a sample image off the ImageJ site, boats.gif. It's 720 pixels wide, 576 pixels high. It has a particular ID, which is just a number that the program has assigned to it so that you can use it as a handle to get at that image. And something about the coordinates, 0, 0, I guess, is at the upper left, and the display range is 0 to 255, and it's not thresholded, and here's the source of it, and so on. And here's, again, that idea of pixelization. If you zoom up an image, eventually zooming doesn't buy you anything because the image has discrete pixels. On the image to the right, I've actually done some smoothing. We'll see about that later. And that makes it look a little better, but it only makes it look a little better because I didn't gain anything by zooming it up, so by smoothing it out, I threw away some of the pixelation artifacts that were created when you just zoomed it up. Okay, now a color image. So that's spectral sampling. A color image typically has, you're used to them with 3 channels, red, green, and blue. And if you look, here's the color image, and you can see that this corresponds to where you have the red, and this corresponds here, the center image, to where you have the green, and here are the blue nuclei. And this particular image was probably created from 3 separate fluorescent channels that were acquired and then merged as a red, green, and blue image. So that's all fine. However, that's not the whole story, because an RGB image is actually a single image with 24 bits per pixel, of which 8 bits are assigned to the red and 8 bits to the green and 8 bits to the blue. If you want to store a gray image as an RGB image, a gray image is also a color image, it's just color gray, in which case it will assign the same weight or the same value to the red, green, and the blue so that it'll look gray, okay? And now, there's another idea, which is called a composite image, which I show in ImageJ. It'll appear with a little slider at the bottom for channels because that's actually a stack of 3 discrete images. And it's important to realize the difference between these two. One is simply 3 images that I happen to ask the computer to display as a color image, and one is an image with 24 bits per pixel that is, where they happen to be assigned a certain way. The reason that's important is because of something that actually happened. This is real data. Somebody comes to me with an image, and this is it. It's got red in it and gray. The gray is a transmitted light image. The red is a confocal image. And there's also green here. I think you might see it over here. And he wants to do some image processing on it. And if I break that up into red, green, and blue, look what we get. We get the gray image mixed into the red and the green, because that's what the system did in order to create this merged image. Now, they could have acquired this properly with 3 separate images. The system they were working on, a spinning disk confocal system, has a little button that lets you choose that option. They just didn't know. So it just did them a favor. It had the default, which shouldn't have been set, and it merged it. It just did this artificial merging. Now what's happened is they've mixed the fluorescence data together with the gray data. Now, all is not lost. Because the blue had no other color in it, I was able to subtract the blue channel from the red and the green channels, and that kind of gave me back what they were really looking for, but there's always a price to pay. And they lost half their dynamic range because out of 256 gray levels, the maximum only went up to 128 now, basically. So it really pays to know what your images, how your images are made, so that you know how to acquire them correctly. Another thing people often do, we'll talk about a little bit later, is they acquire images and they stretch the contrast out because they want to see it bright. And we'll see later that saturates them. Any value that's over 255 in an 8-bit image or over 4095 in a 12-bit image, you don't know if it's 4095 or 10,259. And then, you've lost information. I keep telling people, don't do that. I can ruin the images myself. I don't need for them to do it. It's not. Anyway, here's an example of a composite image, which, something that we took. And 3 channels are displayed. And if I want, I can turn off the gray channel. And you can see that now we see the 2 color images correctly because each image is separate. That's worth it. Then another thing about image representation, color spaces. This is a picture of something that grows outside of the swimming pool at Hebrew University at the appropriate time of year, captured with my cell phone camera, one of the few things I know how to do with a smartphone. And if you break it up into RGB, it doesn't look that impressive, although all the necessary information is here. Here's an example where we've put it into a different color space called LUV or something like that, which is available in image J. And now it looks a little more impressive. This is an intensity scale, and these are 2 color coordinates. And you can see that it very nicely separates out the blue from the background. Now, this is just a question of numbers, right? There are 24 bits or numbers, 24 bits for every pixel that represent these colors, but they've been transformed in a way that they're more useful to us, right? Instead of it being RGB, it's LUV. Right? Just numbers and representation. Okay, other things about image representation, 12, 16 bits or 32-bit floating point. If you've got more bits per pixel, you can have more dynamic range, more discrete values. If you're doing division, for example, then you need to generally go to a 32-bit or to some floating point representation, because when you divide 220 by 100, it's 2.2, and if it's an integer representation, it's just going to be 2, right? And you want to know the difference between 2.2 and 2.3 and 2.4 and so on. So as soon as you start dividing or normalizing things, you need to use floating point, which we have in image J. Multidimensional data, X, Y, Z, T. Lambda is color often. You can have other dimensions too. Lifetime, for example. Every other dimension, multiplies. It's a 2D matrix of values. Fluorescence lifetime, for example, thermal data. I take AFM, atomic force microscopy images, and so on. Okay, a word about about storage formats, file storage formats. So you heard TIFF, BMP, PNG, ND2, OIB, a whole alphabet soup. Thanks to the bioformats people, you can read just about every format that's out there, and that's very nice. There's something called metadata. The machine characteristics are often stored as part of the image, and that's important to know about. And again, bioformats can generally read those metadata, and that'll often tell you how the machine was set up and so on. That's very important. And you don't want to lose it, for example, by saving your data as a BMP image with no metadata attached to it. And usually the TIFF or the others have the metadata attached. Lookup tables we're going to be discussing. A major issue, compression, JPEG. Okay, here's the way it goes for scientific imaging. JPEG, don't save your files as JPEG. Really, I get all kinds of data saved as JPEG. Sometimes they can get away with it, but it's not a good thing to do. because it's a lossy format. You don't get something for nothing. It's nice to be able to take pictures of your family with a 23 megapixel imager and have them come out, stored in 500 kilobytes. Really it is. And they look great, but that's only because you don't really care about all the little pixel variations, and the little hair that goes this way or that way. You're willing to see the overall picture. Here's an example of an original image. And here's a JPEG compressed image, and it looks fine. And here's the difference between the two. Now, you see all these little dots. As far as JPEG is concerned, they're noise. But when I give my lightning talk in the afternoon, they may very well be telomeres, right? Because that's what telomeres look like. They're little point objects and so on. So you don't want to use JPEG when you're doing scientific imaging. Disk space is cheap. Experiments are expensive. It's basically the rule. Okay. Now we have to talk a little bit about how you characterize an image. Someone brings me an image to process, and one of the things I do before anything is I put the image up there and I play with it a little bit to try to understand what's there. And there are two things I will generally look at: the histogram and line profiles. Okay, a histogram is like a probability distribution. It's the number of pixels of a given gray level. So for example, if you have an 8-bit image, there's 256 possible gray levels. And if I want to, I can have 256 bins. And every one of those bins, it will say how many pixels have that level. So you look at a fluorescence image, as I often use. You'll often see that there's a lot of dark in the background, right? So here we go, 0, 1, 2, 3 by 4. You'll see that I'm starting to, here's a nice little peak here. You can see it in the numbers. You can see it down here too in the black. Now, if you were to look at the histogram on a linear scale, you would think that all the action is down here in the black, but that's really the background. So the log scale here shows that there are pixels, in fact, that are bright, and they're actually what interest me. You'll notice, as we'll talk about later, that I don't actually go down to 0. I set my imagers so that I don't really have pixels at 0. And you'll see that I set my imagers so I don't have pixels up at 255 or at 4095. The reason is, if I have my imager set so that black is 0, I don't really know if that's black or, the real 0 is at minus 253, right? And if I have my top up at 4095, then I may very well have values of 10,000 there and not know, okay? In a color image, you might see 3 histograms, one for the red, one for the green, one for the blue, okay? And that's what a histogram is. And the intensity profile is where I take a line and I look at the intensity of pixels along the line. So here's the yellow line, which I hope you can see. I hope it comes out. And starting from the right side, okay, here's a bright cell, right? So I come up here. Now here's another cell. It's actually 2 cells, and you can actually see it come down and go back up. And then I pick up like the dendrite here at the bottom here, and even though you don't see much intensity here, but you see that there's some intensity. That's a line profile. And I can look at this and kind of get a feel right away for how big are my objects, how many pixels. This is uncalibrated distance, but usually it's calibrated. A nice thing to do sometimes is to do a 2D surface plot, right? The intensity is going up, and it's nice and pseudo-colored, and I did it because it's pretty, and you can do this in image J. But this can be handy also. So these are my 2 first characterizations. I look at the histogram and see if my images are saturated or they're too or whatever, and I look at my, also histograms, as you'll see, will tell you sometimes the background is all dark and the images and the objects are all light. We should only be so lucky. And I look at these line profiles to get a feel for how big what are the dimensions I need. Okay, so I already talked about bits per pixel, 256, 4096, and 65, 536 for 16 bits. A lot of cameras now, like the new SCMOS imagers, come with 14-bit dynamic range and 16-bit dynamic range. Humans perceive about 32 to 64 gray levels, which is why radiologists have this thing called the window. They'll set their display window so they can see, hard, bone, or they'll see soft tissue and so on. But so just because we only perceive this doesn't mean that there isn't useful information there, and you should be aware that that's the reason why your users or whatever should not just, stretch their contrast up so that they can see, because, when they can see, they're already saturating out the bright features. Now, with the lookup table, what we're trying to do is map the values of the image into something we'd like to see, like colors or whatever. And here's an example. This is what a typical contrast stretch does. We take this and I say, well, you know, the background I want to be darker, so I map those values to 0. Here they are. And then I have a much higher slope that brings, you know, that makes the intermediate values brighter. And then, you know, I don't have very many values above 165, so I map those all to 255. And now you can see that the image on the right is more contrasty than the image on the left. I have not done anything to the image at this point. That's one of the nice things about this. I have not touched the image. If, however, I use that button called apply, it will map this curve back into the original image, and then I have changed the image. Okay, that's an important thing to realize. And just to drive that point home, this is how you make pseudo-color, right? Pseudo-color is made by mapping different gray levels into colors. So I map 0 into red, goes up, and now I start to bring the red down, but I bring the green up, and now I bring the green down and I bring the blue up, and then I cycle it through. And you can see that the edges are red because they're less intensity, and then blue is the higher intensity. And eventually it comes to white because I've left the blue high and the green high, and underneath here you kind of see how the colors map to different intensities. And this is just numerically, the left side are the original grayscale intensities, and the red, green, and blue values are what they're mapped to. And again, this is non-destructive. I haven't made my image a color image. I've just made it that we perceive more color differences than gray level differences, so pseudo-color is very often used. And your display typically is a red, green, blue display, so these numbers will say how the display will show the image. Okay, so there is our image characterization. I should say, are there questions at this point about, you know, what an image is, or those two concepts, the lookup table and the histogram and line profile, those three? Okay, good. So, image acquisition, I spoke a little bit about saturation and black level, gain and offset. The histogram is used to see if your image is saturated or too dark. And I'm not going to talk that much about image acquisition, but very often your software will show you a histogram in real time of what you're acquiring. And this may be something that you're looking to see. And if you see like a little peak up here at the top, it's saturated, right? You're getting a lot of, you may not care. I mean, it could be that you've got some really points that you don't care about and you saturate them so you can see. But you have to know that that's what you're doing. And if you got a big peak at the 0 here, that means your image is too dark. Okay, your image should sit, you know, most of your pixels should sit in the middle. And that's why lookup tables on many image acquisition devices, confocal microscopes and so on, they've got this high-low lookup table where values below 5 are, let's say, green, and values above, you know, 250 are red, or something like that. And then in the middle, it'll show the grayscale. So here, that's what's been done over here. The red is showing all the saturated points. Okay? If you're doing phase contrast microscopy, you'll often get, you know, your cells divide and boom, you get this very bright phase contrast image, and you have to decide if you're going to set your range to include that or you're going to let that saturate, that sort of thing. Okay. Many imagers have auto range on them, and so you set different exposures and the image looks exactly the same because it's auto ranging for you. But the low exposure, you've got more noise, okay? And at the high exposure, you have less noise. Okay, how many bits do you need? Do you need to pay for those extra to have a 16 bits or something like that? The answer is usually not. But in any case, here's an example of an image where its histogram shows me that all the values are between 200 and 600, let's say a little over 600. I could basically map that to 256 values and operate on it that way. And if I have many images that are, 2.5 gigabytes big, and it kind of makes a difference. If I don't really need them to be 16-bit images, then I'll work on them as 8-bit images, and things are a little bit faster. 16 gigabytes of RAM in the computer just don't go as far as they used to. Okay. Excellent. So the image processing workflow. There are a couple ways to represent that. In this slide, I point out that there's enhancement. In other words, let's make the images look nice. When I have to publish an image or I have to put it on a slide or something, I may enhance the contrast so that it can be seen, and I'll always put in a little, figure caption, contrast has been stretched so that so the features of the image are visible. That's very important. I'll say this a couple of times. I'll say it first. Now, in image processing, you can do anything you want to your images, anything at all. You can put features in there, anything you want. There's only one thing. You have to write what you did, right? So the next guy down the line, whether it's the referee or the person who's trying to reproduce your work, knows exactly what you did. I fudged the data, yes, but write it so that they know that that's what you did. If you're honest, you're okay. So that's, and always keep a copy of the raw data and anything you need to reproduce the entire chain of operations, right? You usually don't have to store all the intermediate images as long as you've stored the scripts, the programs, or whatever that generated them so that you can always regenerate them when it's necessary. Okay. Segmentation is the really hard thing, which is why I'm leaving it to Jan, right? I'll say a little bit about it here, but that's really the name of the game. I'm in business because, segmentation is difficult and every problem I get is a little bit different. If segmentation was easy, I'd have to find another line of work. And measurement is really just bookkeeping in a way. Once you got the segmentation done, measurements are easy to do. There's a lot of image processing software out there, public domain like ImageJ, Fiji. There's, commercial software. MyPev, I thought I put Cell Profiler on here also. I don't know why I didn't get on here, but no matter. There are a lot of them out there, and some of them, they all have different, things that they try to do. The commercial ones tell you that you'll get better support and so on and so forth. My opinion is that everything you're going to do in 2D and even 3D analysis, you can do in ImageJ, 3D visualization, and so on. Some of the commercial packages are faster and more polished and so on. But there are many packages like Gwydion, for example, that's just designed to work on AFM data. And it's also public domain and so on. It's very nice package. Okay, the workflow. So before I spoke in terms of what you might do, there's enhancement to make pretty pictures, there's segmentation to find features and so on. Your workflow typically is a pre-process. You want to remove noise or something. Remember, removing noise is a destructive operation. Removing noise means you are assuming something about your data. It may be reasonable to assume, but again, you have to be upfront about it. We have to do segmentation and classification and measurements and so forth. So image enhancement, they're generally divided into histogram-based methods, thresholding and stuff like that, contrast stretching. You might want to smooth the data if it's very noisy. We'll see examples. You might want to enhance edges, and you'll almost always need to do some sort of background correction. So let's take a look at some of those. Okay, boy, I was sure I'd move this slide. Okay, but in any case, this is an example of contrast stretching. I showed you that before, right? You might want to invert intensity. I don't know why, and even this still happens in ImageJ. There are some operations that assume that your objects are dark rather than light, and the background is light. And I don't know for sure why this is, but I have a theory that this is because in the early days of image processing, when they didn't have nice displays like this and they were printing their images on paper, it made more sense to make your objects dark and your background white so that you didn't have to, print a black background or something like that. But this is inversion. This is thresholding, which really belongs with segmentation. And equalization is a way of stretching your contrast only in the places you really need it. Right? That's more or less what's happening here. So this is an example of image enhancement. You can see here better than you can see here. Right? You might have a neighborhood-based operations, like you look at the pixel surrounding the pixel of interest and make a decision. Right? In this case, we're looking at 9 pixels, 3 by 3, and we'll make a decision, and we'll see some examples. We might take an average, we might take a median. We'll do something, and if we have an outlier, for example, we might remove it. Right? That's a median filter. Okay, so let's skip past this. And this is an example of taking the average of 9 pixels and replacing the middle pixel with that average. That's a smoothing operation. Okay? If your data are stretched out over 100 pixels at a minimum, then you're not worried about variations at the level of 2 pixels. Those variations are noise, and you'll want to average them out or median filter them or do something to smooth them, because the noise is very often high frequency. You know, spatial frequency means the variations in the image over space. So that's why you might do something like this averaging. Here's another example, that median filter I spoke about. Take a neighborhood and replace the pixel in the middle with the median of the pixels around. Now that's a nice operation, because if you average and you have an outlier, that outlier pulls the average off. But if all of your values are somewhere spread out between 15 and 23, and then you got one value that's 97, so replacing that 97 with the median is usually a better bet for, it's a better estimate of what it should have been. I mean, that's really what filtering is about. It's trying to estimate what the original signal was. Okay, so here's an example of, here's the line profile, which is something that I look at and I say, oh, there's a lot of noise in here. I do a median filter and you could see that there's less noise, right? Always there's a price. I mean, median filters are somewhat edge preserving, but they still will, blur your edges a little bit. And also, like, I'm going to show you these telomeres, which are more or less point objects. The last thing I want to do is a median filter. My telomeres are outliers. I mean, that's how they work. So, okay. So here's an example. This is the very same idea. It's called convolution, which I actually skipped the slide. But convolution is a more general way of this type of filtering, where you're looking at the neighborhood and making a decision. And for those of you who have some engineering background, convolution is this linear filter that you can run on 1 or 2 or multidimensional data. So if my kernel, we'll call this the kernel, if it looks like this, it's an averaging operation, because I'm adding all these numbers up and then dividing by their sum, right? So that's averaging. And we can see that the image on the right is somewhat blurred compared to the image in the middle. Conversely, here I've taken a difference. I've taken 9 times the image in the middle, and I've subtracted what amounts to -8 times what's around. Well, not -1 times this one or -1 times this one, but altogether it's -8 times the surround. And it enhances the edges, because where the image is uniform, that's not going to change anything, but where these edges, they're going to get enhanced. Okay? If I put an 8 in the middle instead of a 9, then I would have gotten an edge detector, because then a uniform background would be 0. 8 times the thing in the middle, -8 times the surround. Imagine that all 9 pixels are 100. So 8 times the middle is 800, and then -100, -100, -100, and so on, you get 0. So that would be an edge detector. So by changing this kernel, you can make do different kinds of filtering operations. Okay, background subtraction. This is an important one. At least in microscopy, you never have a uniform background. And I was looking for, my system's too good. I had some systems that, I had some images that the background was really, really convex. But in any case, you can see here the background is not uniform. And there are a couple ways to estimate background. And it can also be measured, by the way, which is really the best thing to do. Anytime you can measure instead of estimate, that's good. But I've taken this image, and the line profile here is along this red line. I don't know if you can see it, but there's a red line here. And there's the same line in all of these. Thank you for the region of interest manager. And the blurred image is simply this image. Well, it's called the Gaussian blurring, but it's an averaging operation with a radius of 30 microns. So that kills the cells, which, if I'm not mistaken, have radii of about 10 microns or so, give or take. And this is my estimate for the background. You can kind of see that this line more or less tracks along the bottom, right? If I subtract the background from the original image, voila, I've got a nice flat background here, and here are my objects. And notice that these objects have cells, and you see these 2 sharp lines, those are my telomeres, right? The little dots in here, those are my telomeres. They're important. They're not noise. So that's taking a radius of 30 microns. What if I take a radius of 4 microns? Well, now that radius is much smaller than the cells. So the background includes the cells, but not the telomeres. So depending on the scale I use, I can choose a different size object, right? What I call background, I should say background is in the eye of the beholder, right? The cell is the background for the telomeres. The rest of the background is the background for the cells and the telomeres, of course. And you can see that now that's worked nicely. If it hadn't worked nicely, I probably wouldn't be showing it to you. I'd find a different example. Yeah, it should only be so easy is what we show you. That's the point. That's why I said the segmentations. You read a paper on some new algorithm someone developed, and then you try to apply it to your own stuff. Anyway, ImageJ has a background subtractor, a rolling ball filter, which is a nice, sometimes it's called a top hat filter or a Mexican hat filter, whatever. Take a big beach ball and roll it underneath this curve and make it big enough so it won't fit into these, peaks, right? And wherever it touches, subtract. So if you make the rolling ball radius 30 microns, then you can see that it's taken the background off but left the cells. And if you make it 4 microns, then you can see it's left the telomeres but taken off the cells. Of course, the noise remains also. After all, noise is high frequency. Noise is something that is not background. So we've done it 2 different ways, and there are a lot of ways to estimate background. There's a non-uniform background removal plugin where you can actually mark areas in the background, and it'll do a cubic spline interpolation and find the background for you, which sometimes you need. And for those of you who are interested, I have a way of automating finding the background for that so that you can kind of get the best of both worlds, that you can get a nice cubic spline of all the places you know are background. I should say, by the way, and for any of these things, this talk and also the next talk, if you see something here that you're interested in doing and you didn't quite see how it's done or something, you can speak to me about it at the conference, send me email afterwards, whatever, and I'll be happy to send you a code snippet or just explain to you what it's about, because there's generally not enough time here to get into the nitty-gritty about how it's done, but almost everything you see here has some kind of macro or scripting script that's been written to do it. Okay, segmentation. There's histogram-based methods. Almost every way of distinguishing background from foreground or from objects, somehow, at some point, you're going to have to deal with histograms and intensity. I mean, the bottom line is you want your objects to be one color or one intensity and your background to be another. Okay? There are edge or texture-based methods. There are region-growing methods. We'll talk a little bit about that. There's morphological processing. There are a few really, really excellent, crucial update sites like plugin things that you should get in Fiji, and one of them is Gabriel Landini's morphology site, right? It won't break anything. There are occasionally, check that one off if you get Fiji and use those. Those are very good. Little plug for, I use them a lot, so I should put in a plug there. And machine learning also, Weka segmentation. So this is the simple, it should only be so simple. Of course, it's an example image from ImageJ. You may know this image. I don't think, I was hoping okay. This is one of the sample image blobs, but you'll notice that this is inverted. Well, it's not inverted. This is the way the image really is. When you download it, it's inverted. Take a good look. It'll see on top inverting loot, something like that. So anyway, here's the image, and it's easy to segment. The thresholder has a number of automated thresholding algorithms built in. They're all based on, analyzing this histogram and finding some kind of a valley between 2 peaks. I mean, in one way or another, that's more or less what they do. And it's marked all of the objects in a red overlay. And then we use the particle analyzer, and we tell it, I've told it to exclude on edges, so it's not mark these guys on the edge. It feeds all the information into the ROI manager, and every one of these is marked individually as an ROI, and we can get thousands of objects, and ImageJ already has them all listed individually, and all these measurements. I don't know if in the next slide I'll show you the measurements that you can do. Okay, wait a minute. Hold on a second. All right, what's not shown here is a results table and the measurements menu, which will allow you to measure all kinds of things. You can measure morphological parameters, circularity, you can measure intensity, you can measure different moments, you can measure standard deviation, you can, of course, area and mean intensity and stuff like that. You can get all that out. That's why I said that the classification is really very simple. The hard part, well, segmentation here is easy, but wait till we see. So it's not always so easy. What happens when your original image looks like this, and there is a big, non-uniform illuminated background, okay? And you try to segment it, and this is what it looks like, right? Subtract the background, and now this is what it looks like, and that's, much more reasonable. So background subtraction is very, very commonly needed in these guys. And okay, I mentioned edge detection before. These are different kernels that will do edges, and there are different ways of finding edges. ImageJ has some built-in edge detectors, and you can find these edges, and then you can fill them in, right? You can segment them and fill them in. You can identify your objects based on their edges. Okay, I have, for these slides, which came from different places, you'll see links at the bottom here that you can click on in order to find the original, so that's all attributed. We can look at texture, right? It's often difficult to segment DIC or phase images because their average intensity is often the same inside and outside the cell, right? They work on basically finding edges, and if you try to do a intensity segmentation, you don't really get a good one. But if you go and do a variance operation, okay, they have texture. So texture means there are a lot of changes. And then you find the variance, and you'll find that it tends to emphasize the cells. And then what I would do following up on this is I would threshold this and then use morphology operations to close up all the little holes and gaps. And that works very nicely. We'll see some examples. Hysteresis thresholding is an example. In my opinion, it can be viewed as an example of region filling. What it does is it says, well, we want to segment with a threshold of, let's say, 20, but doing so picks up all kinds of background here, which we don't want. However, those cells that have that, those cells, in addition, they have background of, they have 20 in them, but they also have strong spots in them. So I'm going to say I'm only going to take objects which contain pixels which are strong. And I can, of course, set the two thresholds. So let's say I set my two thresholds at 100 and at 30. So I'll say, well, my threshold is 30, but only if that object that's found contains at least some pixels that are 100, that are strong. So in the case, for example, of my telomere project, the telomeres are very strong. So I can say I only want you to find, nuclei that have telomeres in them. So that's what this does. So in a sense, it's saying, if it's got that bright pixel in it, fill it out. So that's hysteresis thresholding. It's available in the plugins. I think it's actually, I got that out of the BioVoxel package. Morphological processing. Okay, that's the two operations there are dilation and erosion. Dilation means let's pad it. Okay, let's add pixels to the borders. Erosion means let's peel it off. Let's peel pixels away. You can kind of see, here's your original image. Here's dilated, so it made this little piece here connect. Here's erosion, so it got rid of this little piece, right? And it opened up these holes. So there's something called opening and something called closing, which is erode and then dilate, or dilate and then erode. Mainly, let's do something like this. So now I've connected this little piece to the main image. And now let's erode it back, but it's going to remain connected because it joined up. Or let's do the opposite. Let's erode it, and that gets rid of this little piece. Now let's dilate it back. But what's been eroded away completely is never going to come back. And if you look in the morphology plugins I mentioned, you'll find a lot of nice variations on the theme here. Like dilating, but don't let things join is a very handy one. Or dilate, but only fill a mask. And things like that. There's some very nice, there's also grayscale morphology, which I won't get into. So morphological processing is a very good way. So this just points out what erosion is. Here's the original image, and the green pixels are going to go away, And I won't spend too much time on that because we're somewhat time limited, but this is an example of dilation where I have the original image and I pad it, right? The cyan pixels are what are being padded by the cross. And if my structuring element, that's what the kernel is called, the corners are included, then these green pixels will be added. And this is what we're talking about when we say 4 connectivity, 8 connectivity. The dark blue X's around here, the cyan X's, these are 4 connected, and if you include the corners, that's called 8 connected, and there are times you want it this way or the other way. This is something I made, but I adapted it from this particular presentation. Okay, so this is morphological detection. You can do a lot of nice things with it, like you can of course find edges with it. You can, for example, dilate and then subtract the original from the dilated. You can skeletonize. I use that a lot. You can do this. You can do a sizing, right? Erode. See what went away. Erode a little more. See what left. See what went away. Erode a little more. See what went away, and then you can get a nice histogram of particle sizes, just following that procedure. So it's very nice. Machine learning, very nice also. In machine learning, you point out areas that are the object and you point out areas that are the background. You tell it what kind of properties you'd like. Most of them are related to mean intensity or variations. That's what most of these are. Unfortunately, I don't see in the machine learning the ability to look at long-range structure, but still it can be very handy, especially in like EM and stuff like that. And I used that one time. I presented something on that, I think two conferences ago, something like that, either 1 or 2. I think, yeah, 2. So here's an example where this is a phase image, and we mark in dark, we mark these cells, and we mark the background, and then it figured out this is its segmentation. And it will give you a probability map, so you can decide, do you pay a higher price for false positives or a higher price for false negatives? And based on that, like in my case, I found empirically that at the 50% probability threshold, my objects were somewhat dilated, right? So I said, I'll take a 70% probability threshold. And then, it hugs the objects very nicely. So this is a nice case where that kind of app, and you can apply it after you train it on one image, you apply it to other images, right? You save the characteristics, and you don't need, you have a training set, but once you've trained it, then it will work on other images too. Okay, so that's a very nice thing. Correlation, that's cute, and it's very handy. This is an example of a pattern, and here's an input image. This is kind of an artificially constructed example. I correlate the pattern with the image, which for symmetric patterns is basically like I just use the convolution function of image J. And this is the correlation image, which doesn't look like much, but it turns out that wherever this pattern correlates very nicely with something in the image, I get a peak. So I looked at the first 3 peaks, and indeed, I don't know if you'll be able, okay, yeah, I guess you can see it here. So this is 1, 2, and 3. It found 3 such things that were similar to the pattern. Now, finding 1 was not difficult because I took the pattern off of 1. However, 2, that's pretty much a nice little circle of about the right size, and yeah, it found it. 3 is not a circle of about the right size, but it found it because 2 different parts of this surface, how shall we say, conspired to make something that looks like that circle. It's never perfect. I think I saw this on an email from Kenneth Sloan. I don't know if he's here, but anyway. He said 85% is trivial, 90% is a thesis, 95% is a career, and 98% is impossible. Or did he say, or maybe 98% was a career and 95% was a thesis? I don't know, but you get the idea. But this is very handy because I was looking for, DNA combing produces these lines that are all broken up, and the Huff transform doesn't work very well on them, and so on. And doing correlation with what they call this DNA barcoding was actually a pretty good way to find these DNA barcodes in this very noisy DNA combed image. Okay, object classification. This is the slide I thought I was going to have earlier. Set measurements. So you can set up all these measurements, the best fit ellipse. For example, I took a Fourier transform, well, whatever, that's just, I won't say now what a Fourier transform is, but you can find angles in a Fourier transform. And it's good at finding periodic line structures, right? So this DNA combing experiment produces a lot of lines. I don't have the image up here, and the lines are supposed to be parallel and are supposed to, but they're not always, but they're close, and they're not always flat, horizontal or vertical. And if you have to find lines that are not always horizontal or vertical, it's a little bit of a pain computationally. So what I would do is I took the Fourier transform and it produced a feature that was 90 degrees, 90 degrees perpendicular, in other words, to the lines of the DNA. And I used this best fit ellipse thing to find that line, because it was also, I couldn't just use the angle of the line because the line was also kind of noisy and messy. But the best fit ellipse did a nice job. And then I knew my orientation and I rotated my image accordingly. So that worked very nicely. You can get perimeter, centroid, bounding rectangles, shape descriptors, and so on. So there's a lot you can measure here, and then it can be used to filter out non-images, which is like roundness is a very good one. You get rid of artifacts because the nice cells are round and the dying cells are broken up or something. It's actually the other way around in nice cells. The dying cells are like balled up and the good cells are kind of stretched out. So anyway, that's classification. So let's look at an example here, blob detection. So the image is clean. You can segment the objects from the background. Global thresholding works. You can classify the objects. You can decide on a certain size. And there you go. And here's our results table. No, you don't have to copy down all the numbers. I just wanted to give you an idea. You can look at it on the slide. But you get all these measurements. And for example, most of the blobs are fairly round, but some of them are really like overlapping. And then I show a watershed filter can divide them. Divide them. There are a few filters like that. That's also a morphological filter. And another example is a time series. Okay, come on. There it goes. It's supposed to. Okay. You might have noticed that it got bright at one point. Okay, yeah. This is an example of intensity versus time. This is a chloride indicator, and it shows the cell was given something that opened up the cystic fibrosis transport the receptor, and wow, you had all this chloride. So that's just another example. I didn't touch much on time series and so on. Okay, that's perfect. Other issues, I didn't so much get into visualization. I use ImageJ basically for analysis. But the flip side of that is visualization, which ImageJ can also do, although as I mentioned, for 3D and multidimensional visualization, some of the commercial packages are cleaner and are more robust, and they let you do things quickly. Analysis in higher dimensions, of course. You're going to hear also about ImageJ2 and how all dimensions will be created equal. I guess that's one of the major points there. But in any case, you can have multidimensional data, and that means these data can be very large. And I said 16 gigabytes just doesn't go as far as it used to. I often am loading up data sets that are, multi-gigabytes at a time, and it can sometimes take a while to process. Okay, and some references. Wow, and 4 minutes to go. So if you have any questions, yes.
Is there a resource somewhere that has example images?
Yes.
A bunch of different types, and then how they're processed, and be a tutorial that walks you through each of those?
Okay. First of all, the ImageJ documentation on that link there has a lot of good stuff like this, and ImageJ itself has a lot of example images, many of which I took from here. There are others which I don't know offhand, but I've seen it both on the confocal microscopy list and Image J. There are banks of example images, and if you search in the mailing list, people have occasionally asked, and you'll find that there are such images. There are a variety of tutorials available. Most of the stuff here is shamelessly, well, I shouldn't say most, but a number of the things here are shamelessly, lifted from other places. But again, I documented it at least. This site, for example, has a lot of that. Just a search on the web will find all kinds of examples. I've recently gotten into Python scripting because you can use the API and it's does some things much nicer than the macro language. And I found a whole bunch of nice examples of Python scripting and how to do that with the API. Java, there's even more. So yes, there is a ton of things, and I can show you a few of them afterwards. Before I forget, it's always something I forget. I have to thank the organizers for making it possible for me to come and for organizing this whole conference. And I have to thank all of you for listening to me politely for, like 58 minutes. All right. And still apparently being awake, but that's because they didn't turn off the lights. Okay? All right, thank you.